Hello, my name is Callum Urquhart and I'm the Global Business Manager for the Energy segment within Atlas Copco. Today I'm going to introduce to you a concept that we call Smart Connected Bolting, which is the implementation of smart factory thinking into the field-based operational environment. We believe that there are significant advantages to be gained in the wind industry by applying smart technology and solutions not only in factories, but also in construction, commissioning, and in maintenance. The smart factory is a term we all know well and is used in reference to the implementation of Industry 4 in the manufacturing environment. Significant benefits such as improved quality, higher productivity, and cost reduction have transformed manufacturing in recent years. Wind energy is catching up with the use of smart tooling in most new manufacturing facilities. But what happens in the field where a significant amount of critical bolting operations take place that have a direct impact on turbine performance, reliability, and cost? The reality is that in many cases, conventional bolting methods are being used due to old processes remaining in place, outdated tool fleets, and a general lack of awareness exactly how smart factory thinking can really be applied in the field with the technology and solutions available on the market today. In order to really capitalise on the full value Industry 4.0 can bring, the wind sector must now drive a transformation in how critical bolting is done across the full value chain. The wind energy sector can be broken into three main areas. The first being manufacturing, followed by construction or installation, and then of course maintenance, which may continue for many years. As we have already said, the terms Industry 4.0 and Smart Factory are well known within the manufacturing, so let us first take a look at how Industry 4 is being implemented in assembly in other industries. Industry 4.0 stands for the fourth industrial revolution. The first was the introduction of mechanisation, such as the steam engine, to replace manual work in the second half of the 18th century. The second was the electrification and the division of labour from 1870 onwards, symbolised by the assembly lines of Henry Ford. The third was the introduction of computers and automation for the production processes in the 1970s. And now, in the current time, Industry 4.0 is the cyber and physical systems merging, the real and virtual worlds merged in production. Let's now consider how this looks in a typical assembly line today. For easy reference, in this case, we will use an automotive production line. As you can see, the cars move along through the production line from one workstation to the next. In each workstation, work is carried out by tools and equipment that have integrated sensors and communication capabilities. This enables data and information to be sent to and from each workstation. This can provide instruction on what needs to be done or document the results of what has been done. The connectivity of the system means that tools, equipment and systems are communicating with each other to optimize performance of the production line and ultimately the production output. If we look even closer at the assembly line and move into a typical assembly workstation, we can see the types of solutions being used to carry out the work. A workstation consists of the tightening or fastening tool itself, such as an electric nut runner, but this is only one part of the solution. The tool also has a controller, which is the brains of the system and can enable multiple tasks or operations to be programmed or configured. To start the work, the operator has a barcode reader integrated into the tool, and he must scan the vehicle identification number before the tool will become active. There is an HMI that provides on-screen guidance on the tasks that need to be done and the order that it should be done. Furthermore, there is a tool selection trays with different sockets which can guide the operator which socket is needed on which application. During the entire work, status can be viewed by the operator using visual light towers or feedback provided directly on the tool or in the HMIs. This ensures that the right work is done and no mistakes are allowed to pass through. It also ensures that if any errors do occur, then the operator is guided how to rectify it. In all of these instances, there is a digital record of exactly what has been done, which can be traced back to the specific vehicle, equipment, parts, or even the operator. All the data that is collected in each workstation can be sent via the factory network to a central location, or indeed any location which is connected. This provides full traceability of all fasteners in the vehicle, which can then be stored for the full life of the vehicle. Not only does this provide a record of what has been done, but by gathering other data such as statistical error reports, failure trend analysis, or tightening graphs, then the data can be used to identify potential problems early, before they happen, or to detect quality defects in components, or even establish that tools or equipment need to be repaired or maintained before there is an unexpected failure on the line. These benefits not only provide peace of mind, but enable continuous process optimization, resulting in reduced quality costs and improved quality output. Smart connected assembly and manufacturing has created many benefits. Industries such as automotive and electronics have experienced great improvements in productivity and quality control from digitization in production. This is why we see that today's products such as cars or smartphones are more complex than ever, but are produced at lower cost and with a quality level far above levels we've ever seen before. Use of smart tools with integrated sensors such as transducers, angle encoders and gyroscopes enables right first-time production and full traceability. Interconnectivity enables sharing and analysis of data across departments and even locations in real time. If we consider the wind industry, we can see in new production facilities such as nacelle or gearbox production that smart tooling and systems are now being used. This image shows a real plant where advanced electric nut runner systems are being used, which has an HMI for the operator, sensors in the tools, and status lights above provide direct feedback. There are also controllers connected to a factory network. This is very much in line with other industries and shows that wind OEMs also start to see the same benefits of smart tooling within a manufacturing environment. But what about the operations and maintenance? The potential benefits are huge by using technology and process available on the market today. In the field, if we could increase productivity, reduce the number of defects, and increase the uptime of equipment, this would result in extremely happy wind OEMs, operators and owners by ensuring that turbine and farm output is maximised. So why haven't we seen this happen yet? The reality is that in the field there are challenges due to the work environment that differ from those inside a factory. On site, safety is a priority due to high torques, working at height and heavy tools. Also, time is money because of crane time, ship time, weather windows and project deadlines. And it's extreme work environments with extreme temperatures and very remote locations. The work environment has many different tool types to secure bolts, such as hydraulic wrenches, bolt tensioners, electric nut runners, battery tools, and even manual torque wrenches. These use very different technology and even have their own unique process. Furthermore, these are often supplied by several different manufacturers with their own technology, resulting in added complexity for operator training, calibration of equipment, and tool maintenance. This creates a significant challenge when it comes to documentation and traceability, which today is mostly done using manual methods. There is no doubt that the human factor will affect the results, and so the combination of difficult work environment and complex tool procedures can result in documentation that is prone to mistakes. And when it comes to critical bolting, mistakes can be catastrophic. In order to reduce the risk of mistakes or errors in the field, there are well-established processes in place to control that work is done in the right way. However, failures still happen. This is because the work is labour-intense, manual operations are carried out by humans who are error-prone, information is often in silos and not shared transparently between parties, and there is a lack of real traceability. It is the goal of all stakeholders to eliminate mistakes and secure that processes are followed. But to understand how this can be achieved, first we must consider some of the basic theory around bolted joint assembly. When we think of a bolt, we can think of it like a spring. As the bolt is loaded with force, it acts like a spring and stretches, producing clamp force, which holds the components together. Although we want to measure the clamping force, this is not easily done, and so typically we measure torque by rotating or tension by stretching, since these can be correlated to the force needed to secure the joint. Applying torque is the most common because it is a well-known process that can be well standardized. However, the results of using torque can be affected by friction. The most common alternative to torque is tensioning, which can be more accurate because it is not affected by friction. However, load losses can occur in the process. These two methods are used in almost all fasteners inside a wind turbine. For example, tower sections are typically torqued and foundations and blades are typically tensioned. If we consider the torque method, we have to think about material variation. So when we apply a torque, the torque increases as the force on the lever increases. However, when the bolt is turning, it creates a friction in the threads and under the head. Since 90% of applied torque is used to overcome the friction, it means only 10% of the applied torque results in clamping force. This in itself is not an issue, since it's known and joints can be designed for this. However, the material variation can play a part. For example, any lubrication added to the parts will result in less friction and subsequently a higher clamp force. Vice versa, removal of lubrication could have the opposite effect. Likewise, external factors such as temperature changes can affect the material properties, resulting in friction changes that will ultimately change the resultant clamp force in a joint. The challenge, therefore, is how to know if there has been any change in the material properties. If we look at this graph, we can see how the tensile stress is built up in a bolt as it is tightened. As the bolt turns or is stretched, it is in the elastic zone until it reaches its yield point, which is the optimum point in the bolt where the stretch is creating the highest clamp force. However, if we continue to stretch a bolt beyond the yield point, it will move into the permanent deformation zone, which means that it cannot return to its original form and ultimately fails. This means for the best performance of a joint, we should aim to be as close to the yield point as possible without going over. The challenge here is how to ensure that tools and equipment used are accurate enough to achieve exactly the right result time after time. When talking about the torque method, we have seen that the turning of the bolt creates a friction in the joint. Therefore, if we can not only measure the applied torque, but also measure the angle of rotation, then this would help us to secure that not only is the right torque being applied, but also that the material variation is consistent. For example, we can detect any changes in friction that may occur. The examples here show the following. The first graph on the left shows a tightening which is exactly the right torque and angle. This means that we know that this joint is okay. In the second chart, in the middle of the picture, it shows a tightening which has the correct torque, but the angle is low. This could be the result of increased friction due to damaged threads, for example, which would result in insufficient clamping force and a loose joint, even if the correct torque was applied. The third graph on the right shows once again the correct torque, but in this case the angle of rotation is too high. This could be due to excess lubrication on the bolt, which could then result in the bolt going beyond yield and ultimately failing despite the right torque being applied. What this shows us is that in order to secure the right bolted joint assembly, you cannot rely on applied torque alone. As we have seen, the torque method can result in challenges to secure the correct clamp force. This is why we often see the use of bolt tensioning in applications which are extremely critical or under extremely high load. Bolt tensioning uses hydraulic pressure to stretch the bolt without rotating it, and as such this eliminates the effects of friction. This can result in achieving very accurate results, which are very consistent if the process is followed correctly. The key part of tensioning process is of course the pressurization that creates the elongation and tension, also known as the clamp load. But tensioning consists of many more operational steps, and they are all critical. What if the operator simply forgets to lock the nut after pressurization? That would lead to zero clamp load in the joint. This is not an uncommon mistake, as we have heard from many operators, and so this creates a challenge in the reality of the work environment. So, although tensioning may be seen as a more accurate means of achieving desired clamp force, the process is more complex and it relies on several manual steps with a lot of human interaction. What we can conclude from this is that independent of which tightening method is used, i.e. torque or tension, the result is fully dependent on both the right material being used and the correct process being followed. To ensure this, tools and equipment that can measure the material variation, such as torque and angle, and can give feedback to the operator on process steps, must be used to be sure that the result is according to the desired specification. Manual tools and human operators provide too many variables and risks. Even if operators have been trained on the right process, material factors can also influence the result. To mitigate these risks, the use of smart tooling with integrated sensors and process guidance can address these needs today, regardless of the method used, torque or tension. There is a global trend toward digitization in most industries. The transformation level and speed is of course different in different industries. This is a ladder from an article in the Harvard Business Review describing a study of transformations in different steps. Examples of transformation related to bolted assembly are, first, monitoring, where we can monitor torque, angle, load, temperature, time to understand what is happening in the joint. Then there's control, torque, angle, load, batch or rehit, where we can control the process to secure that things are done correctly. Then there's optimization using data analytics and intelligent service indicators to improve performance and equipment and service life. Then we have autonomy, the use of automated bolting tools and systems to remove the human element and create even greater efficiency. We believe there will be a transformation in the energy segment, but it's difficult to predict at the speed at which it will happen. It very much depends on how quickly OEMs adopt the mindset that smart factory thinking can and should be applied in the field. When considering why smart factory technology has not been widely adopted in the field-based environment so far, the answer is that technology enablers were not in place until recently. To utilize sensors, communication and connectivity in the field, it was not only necessary to introduce smart tools, but also the infrastructure to connect and interact with the products to gain the true advantage they offer. Technology advances in the area of smart devices, mobile connectivity and cloud computing creates the new possibilities today and has enabled the transfer of smart factory solutions into different work environments. One simple step to introduce smart tools into the field is to identify applications which require not only the correct results such as torque, but also can benefit from process control. For example, wind tower sections are typically assembled using the torque method. Historically, hydraulic torque wrenches would have been used, but these are notoriously slow to operate and they don't have direct torque measurement. Furthermore, there remains a strong reliance on the operator to follow the right process. This can be complex when there are up to 100 bolts per flange to be tightened. Introducing smart electric and battery tools to this application can secure it is done both quickly and right first time. Since the assembly process requires many bolts to be tightened in a defined sequence, the tool can guide and count the bolts. Integrated sensors measure all parameters of the process and provide feedback to the operator in real time directly on the tool via HMIs. Then the tightening data can be transferred automatically to a mobile device that connects directly to a tool, allowing digital record to be saved and shared instantly at the time of application. By using tools with sensors built in and capturing a digital record of the work being done, which is then connected to the equipment that did the work, there is a full traceability of the process data. Process and tightening data can be saved and shared with other sites or stakeholders. For example, all tightening data collected during construction could be shared with commissioning team or service crews. This could result in a reduction in the number of service checks needed. Real-time data on bolt and process status can be collected, analysed and shared instantly, even today, enabling rapid problem resolution and continuous process optimization. This very simple example shows how on the surface it appears that the job was done correctly with the correct torque, but there is a defect that could cause a problem in the future. On the graph we can see that 2 tightenings have been done, which have been built up in 3 steps. In each step the final torque achieved was the same. However, in the first 2 stages we can see the torque curve was different. This is an indication that there is a variation which could be a material defect that could result in a failure at some point in the future. Having this visibility allows us to check this in more detail and repair if necessary, before a much more significant failure occurs in the field. Data analytics can identify this and resolve potential issues before they become major problems. Smart connected bolting can realise huge benefits for the wind sector if applied across the full value chain. Reductions in construction and maintenance time, right first time construction with reductions in rework, predictive service in tools and equipment will increase uptime, digital documentation leads to less manual operations and full traceability, and data analytics enables continuous process optimization. Solutions and technology to make this a reality are available today, but the first challenge is to create a culture change in how bolting work is done in operations. Industry 4.0 solutions and smart factory thinking must also be applied in the field. If this can be achieved, the benefits will have a major impact on quality, productivity and cost reduction in exactly the same way that have transformed the other industries during past years. Thank you for your time. If you would like to learn more about smart connected bolting or to get a live demonstration of the solutions mentioned in this presentation, please contact your Atlas Copco representative and we will be delighted to help.